Hello, everyone. Thank you so much for joining us today. My name is Chris Renton. I am the Associate Director of Marketing and Communications here at the Yale Peabody Museum. This is the last of our scheduled tours of the third floor here at the museum. You've made it around with us to the bird hall, through the dioramas, and now we're going to end here in David Friend Hall with our collections manager, Stefan Nicolescu. So thank you all for joining us today, and for any of you that made it to our other tours, we appreciate you coming along for the ride. Obviously, we had hoped that we would be open through the summer in order to let everyone come back through one last time through the Peabody Museum before the renovation began. Unfortunately, in many ways, COVID had other plans. So we want to do the next best thing, and we thought we'd do some of these admittedly low-tech tours of the exhibitions before we begin to deinstall all of them. If you don't already, please do follow us on social media. We are active on Instagram, Twitter, and Facebook. And if you're not already signed up for our email list, please do sign up. You can go to our website, peabody.yale.edu, scroll down, click on Connect, and submit your name and email address, and you'll get invitations to other programs and events just like this one. Speaking of social media, for the next month, in celebration of Hispanic and Latinx Heritage Month, we are hosting our 18th annual Fiesta Latina event. We'll be doing video programming, regularly publishing videos on Tuesday afternoons and Friday mornings. So meet us there for some great video content being produced by wonderful colleagues of mine. Finally, some ground rules for today. We have disabled the chat function. I'm sorry, but we have enabled the Q&A function. So please use that to pose any and all questions to Stefan. We will try to get to as many of them as possible. If we don't get to your question, please do email me, and I'll make sure Stefan gets you an answer ASAP. Lastly, we are recording this, and it will be posted to our YouTube page, hopefully next week if I can get to it. But without further ado, I want to kick off this tour with Stefan Nicolescu. So thanks for joining us, and enjoy.
Hello, everybody. So welcome to the Yale Peabody Museum, to our latest gallery that we installed in the museum, which seems now quite a while ago, 4 years ago. And I want to start with that beginning and with another beginning after that. So that beginning was thanks to the generosity of Yale alumnus David Friend. He graduated Yale College in 1969. And thanks to his generosity, we were able to renovate our old auditorium. Some of you might remember that, and change it into a spectacular display room for minerals, but also it serves as an auditorium when we need it. And we affectionately sometimes call this room the Minatorium, Mineral Auditorium. So if it wouldn't have been for Dave's generosity, we would have had something else in place here. The other beginning that I want to start with is the beginning of the solar system. And you might think, wait, we are supposed to talk about minerals. Well, guess what? Meteorites are made of minerals, and the meteorites are the leftovers from the beginning of the solar system. So everything that is in the solar system today, from the sun and all the way out the Kuiper belt, was already present in the protoplanetary disk. And I have here a very special meteorite. You can see its name, it's Murchison. It was recovered in 1969 after it fell in Australia. And this is one of our ancestors. So what you see in here, the white specks in the meteorite, those are the oldest objects in the solar system. Those have been dated at 4.567 billion, with a B, years. Also, this meteorite has about 70 amino acids in it, which
are the building blocks of how we know it life, but these amino acids in this meteorite were generated by inorganic processes. And it also has tiny little diamonds, nanodiamonds, which are pre-solar in age. So these were inherited from the supernova that was in this part of the galaxy before the formation of the solar system. So think of this like of meteorites and interplanetary dust as flour, sugar, butter, a little bit of milk, a little bit of salt, that those who know how to make them prepare chocolate chip cookies. So that flour and the other ingredients for chocolate chip cookies are placed in an oven at a certain temperature for a certain time. And through time and chemical transformation, we end up from the basic ingredients with chocolate chip cookies. Same thing with meteorites. These are the ingredients that through time and transformation ended up with everything in the solar system, including us. We are the chocolate chip cookies of the solar system. So with this, let's move into the David Friend Hall and see what happened in time from the ingredients in material like this. So as we go in, the visitors are greeted gigantic quartz crystal that comes from Namibia. It weighs a whopping 862 kilograms or 1,900 pounds. And it is, in geologic time, the oldest specimen in the gallery. It's roughly 600 million years old. Minerals are defined as being naturally formed solid objects with defined chemistry and internal ordering or crystal ordering. But minerals, the same mineral species, can come in many colors. And then we have mineral varieties. So quartz like this is called milky quartz because you see it's not completely transparent. The light makes it look like honey colored, but it's really an off-white in color when it is not, what am I about to say? When it is not backlit. So if some of the silicon in the quartz is replaced in minute amounts by other elements, we end up with quartz varieties. And we have a beautiful example behind us, this amazing amethyst geode that comes from Uruguay. And the purple color in amethyst is determined by tiny amounts of iron. So mineralogically, it is quartz amethyst variety. It's much easier to say amethyst than to say purple colored quartz. When we say amethyst, we know exactly what we are talking about. Quartz comes in many shapes and sizes. So another beautiful example we have here in the gallery is the specimen in this oval shaped case, which is a sandstone concretion. It's basically a rock formed by cementing loose sand grains. This specimen comes from southeast of Paris in France, from Fontainebleau. Fontainebleau is known for many things, but from a geological point of view, for its large sand deposits that have been used for centuries for manufacturing glass. So many stained glass windows in from Fontainebleau sand. In certain conditions, the sand grains are stuck together and they form these absolutely amazing shapes. The Fontainebleau glass, the latest claim for big fame, came in 1981 when the glass panes in the Louvre Museum's glass pyramids were manufactured from the sand that also was the source of this beauty here. And if we are at this part of the gallery, let's move. We have questions?
Yes, thanks, Stefan. We have a couple of questions. One about what you said earlier. This person, Katerina, is wondering, how do we know the origin of amino acids that are in these minerals? Is it from background information?
No, it's analysis. So the meteorite has been analyzed and the amino acids have been determined. But because amino acids, organic compounds, can be generated by inorganic processes as well, and because we don't know for the time being of life anywhere else in the universe except on this third rock from the sun, we can certainly conclude that those amino acids have been formed by inorganic processes.
Thank you, Stefan. That's great. We have one question now about the formation that we're looking at now, and that is, why is the sand so pure in this particular object?
Because it went through, so sand forms by erosion from rocks that contain, in this case, quartz. And by repeated sorting, natural sorting processes, the quartz is separated from the other minerals that are disintegrated from those rocks, and it's basically concentrated. You have to imagine that this is a huge process that takes place over geologic time. So it doesn't happen instantaneously. And through these repeated sorting and accumulation, we end up with mineral separates. And in this case, the mineral separate was quartz grains. We do the same thing in laboratories when we want to analyze specific minerals for specific analysis. So we many times need a certain mineral from a rock. We grind the rock up. We separate it with heavy liquids, so the different components float at different densities in the heavy liquids that can be adjusted for density, separate them, and then if we need to further purify them, we can use also magnetic susceptibility and separate them in magnetic separators. So let's move to the next case here behind us. So this is an array of beautiful specimens from many parts of the world. By the way, the vast majority of the specimens here in the David Friend Hall, by number, are on loan from world-class private collections. And we are very, very grateful for our lenders for allowing us to showcase their beauties. So the one that I want to focus on here is this green needle-shaped aggregate of crystals. So I don't know if you can see the name there of the mineral. It's a tongue twister, but it's actually quite easy to say, Skłodowskite. So it is named for Maria Skłodowska-Curie, who discovered radium and did a great work at the beginning of the 20th century in radioactivity. And because it is the copper correspondent of the mineral Skłodowskite, it is named Skłodowskite. Minerals can be named after a person, after a place, after composition. So there are no set rules for the approximately 5,500 mineral species that are known today. So this is a radioactive specimen, but it is at a level of radioactivity that it is really safe for all our visitors. Otherwise, I wouldn't stand so relaxed in front of this cabinet talking to you about it. The specimen next to it, to its left, looks like velvet. And it is a little bit misleading because we think of velvet as something very light and pleasant and easy to lift. The mineral is called Motramite. And if you look at the chemical formula there, you see that it has lead, copper, and vanadium. Copper and vanadium are transition metals. Lead, it's an even heavier element in the periodic table. And actually, this Motramite specimen is quite heavy. So appearances sometimes are deceiving if you don't know what you're dealing with. In the next case, we have a stunning specimen of Albite. Albite is a member of the tourmaline family. This one comes from Brazil. And that white mineral that surrounds the big crystals of tourmaline is a member of the feldspar group. It's called Albite. So it's a little bit confusing. We have Albite in Albite, but they are spelled differently. So Albite is E-L-B-A-I-T-E. It's named after the island of Elba of Italy. And Albite, its name comes from its color. Albus in Latin means white. Now this particular shape of Albite, bladed Albite, has been named at the beginning of the 19th century after Parker Cleveland, named Clevelandite. Parker Cleveland was a professor at Bowdoin College and the contemporary of our own, of Yale's, Benjamin Silliman, who was Yale's 9th professor and the first professor of mineralogy, chemistry, and geology at Yale. The vast majority of the specimens in this gallery are very colorful, with the exception of maybe this one. I affectionately call it the ugly duckling. It is a specimen of burnonite, and this was one of my few requirements to borrow and to put on display here. These crystals, so it's basically a sculptural assemblage of several big burnonite crystals. It comes from Bolivia. And I cannot praise enough our exhibit designer that worked on this, Laura Friedman, who very cleverly placed it next to one of the most stunning specimens visually, the fluoride surrounded by calcite on two sides and sprinkled with pixie dust. That pixie dust is fool's gold or pyrite. Do you have more questions?
Thanks, Stefan. Yeah, we have two questions actually. One of them relates to the exhibition design. You just mentioned that. This person would like to know why we haven't included additional interpretation about specimens and just sort of minimal identification. They were wondering what caused us to make that choice.
So that is a sort of an experiment that we are running with the visiting public, because we wanted, first of all, to have a visual and aesthetic impact on our visitors. That's why the light is designed as we have it in here, focusing on the specimens, and minimal information, so you can take a picture of the name of the mineral. You have there also the chemical composition, and we also recognize our lenders by mentioning them on the labels. And then those really interested can easily look up information about the locality or the specimen, I mean the mineral species, and learn more about it.
Great, thank you. We also have another question about the shapes. Richard would like to know what determines the shapes that we're seeing. Is it the structure of the crystal, something environmental?
So in the shape of the crystals is determined by chemistry, physical chemistry, and physics. That's the very general answer. So different ions have different sizes, and they have also an electrical charge. And the combination of the electrical charge with the size of the ions determines the size of the site in the crystal structure. And those are populated, those sites are populated following these rules. So basically, the atomic and molecular ordering in the mineral determines the mineral's shape. And that is respected from microscopic level to macroscopic level. And speaking of shapes, actually, we have a good example in this other case. These are all specimens of rhodochrosite. Rhodochrosite is the manganese carbonate. And we have 3 parts of the world here represented by rhodochrosite. By the way, we have about 28 countries represented by specimens in the entire gallery. So the rhodochrosite that Chris is focusing on now comes from the very famous Sweet Home mine in Colorado. And you see the shape of the crystals are sort of distorted cubes or parallelogram faces. They are called rhombohedrons. The one to the left of it is more blade shaped, and it comes from China. But exactly because of the ordering and the constraints put by physical chemistry on the way that the atoms are arranged, although the shape is very different from the one from Sweet Home mine, the Chinese rhodochrosite has the same dominant forms on it. You might not see it right away. They look tabular. But one of the basic rules in crystallography is that for the same mineral species, crystal faces that are adjacent to each other are at the same angle. This is called the law of constancy of angles. So if you look at the angles on the rhombohedron from Colorado and the angles between the faces on the tabular crystals from China, they are always the same. And then on the back panel of the case, we have 2 cross sections through a cluster of stalagmites of rhodochrosite from Argentina. So you should imagine that actually the stalagmites, those are the speleothems or the cave formations that grow from the ground up. So these grew in this orientation from the wall towards us. And then they were sectioned perpendicularly to the stalagmites and were polished. And we can see the internal concentric structure of the stalagmites. They look in my book like a pair of a little bit oversized, very healthy lungs. So if we have what we like to call a pink period in this case, next we move to the blue period. And in this case, we have 3 different mineral specimens that are sharing the same shades of blue. So the one on the right that Chris is focusing on now, this is an aragonite specimen from China. Aragonite can be many colors. It's very seldom, though, that it is blue. And in this case, the blue color is determined by small amounts of copper in the crystals. Then to the left of it, we have a beautiful assemblage of 3 beryl crystals. The blue beryl, Gemmy blue beryl, is called aquamarine. It's a variety. Aquamarine, it's a beryl variety. Remember how we started with quartz and the varieties, milky quartz and amethyst. So the blue beryl is aquamarine, and it is again on an assemblage of clevelandite, the blady albite, and quartz. To the left of it, we have one of our own specimens. So everything else that I spoke about so far were specimens on loan, but these columnar and botryoidal crystal assemblage is the mineral smithsonite. Smithsonite is a zinc carbonate, and this comes from a very famous mine in New Mexico, the Kelly mine. To the left of it is one of the most spectacular aquamarine specimens that I saw. It is an assemblage of about 80 individual crystals of aquamarine. And I jokingly say that this aquamarine doesn't know that it is a stibnite. You'll understand in a second what I'm, or a little bit more than a second, of what I'm referring to when we'll have a look at one of the stibnites that we have on display here. So stibnite is a totally different chemical composition, but it usually forms assemblages of many needle-shaped crystals. The funny thing about this specimen, it's just a story. It might be true, it might not be true, but it is that it has been found in the roots of an uprooted tree in Pakistan. So even if it is not true, it makes for a good story. And to understand why I make the comparison in its morphology with stibnite, let's move back just a little bit to a case that we passed a few minutes ago, but I guess we'll get there after Nicole tells me a few more questions.
Yeah, I do have a couple more questions. Thanks, Devin. You may be telling us about this a little bit later, but we do have some questions about where the color originates in all of these crystals, especially after showing these very colorful sections.
So the color in the crystals depends on the chemical composition. So there are 2 big groups of colors in the minerals. One is called isochromatic. The other one is called allochromatic. I'm throwing big words out here. So isochromatic means the same color all the time. So think, for instance, of galena, which is the lead sulfide, or fool's gold, which is iron sulfide. Those minerals are always the same color. Whereas the color varieties that I mentioned until now are determined by tiny little substitutions in the crystal structure. So for instance, titanium and iron in a beryl gives it the aquamarine, the bluish color. Chromium and vanadium in beryl gives emeralds, the green color. Iron in amethyst gives amethyst its purple color. Another way that color in minerals changes is by having physical inclusions. If you remember, I mentioned milky quartz at the beginning. So that big crystal of quartz at the entrance has myriads of tiny microscopic, what is called fluid inclusions, which make it that color, and it make it basically opaque. It's not transparent like rock crystal would be. And so, for instance, in the aragonite here, the color, as I mentioned, is determined by tiny little amounts of copper in the crystal.
Great, thank you, Stefan. That's a wonderful answer. We do have one more, a difficult question. Do you have a favorite piece in the collection, and what is it?
I have 2 boys, and I love them the same. How can I choose between so many beauties here? Well, actually, I do have favorites within the minerals, but it's not related to the beauty of the minerals, but to what they can tell us. So minerals and rocks are just like books. So if you know the language, you can read the book. So two of my favorite minerals, actually three, let's put in three. Because of the information that it can be extracted from them and which tells us about how they formed, under what conditions, at what time. So one is garnet. The other one, so you probably are familiar with garnet because it's also a gemstone. The other one is zircon, which is a zirconium silicate. And it is literally not just a book, it's a library of information. And then diamonds, but I don't like well-shaped, clear, or beautifully transparent colored diamonds. I like the ones that are ugly and useless for jewelry, but the inclusions in them tell us about the conditions under which they form at hundreds of miles inside the earth. So, okay, I don't have a favorite one. I have three interesting ones and several more thousand that can be useful. So we were on the way to stibnite. So you remember I said about that aquamarine that it doesn't know that it is actually a stibnite. Here we have a tiny specimen of stibnite. So that tuft of needles is the antimony sulfide on dolomite. Dolomite is the magnesium carbonate. And that specimen is a little bit close to my heart as well because it is from my home country. So I'm originally from Romania, and this stibnite comes from the north of the country, from a historical province called Maramuresh. And speaking of colors, let's take a diagonal trip across the gallery because I want to show you how different aragonite can be depending on where and how it forms. So that aragonite was blue because of copper, but these two specimens, the first one here, these we call affectionately either the bird's nest or Chinese noodles. This is aragonite as well, and these formed in a void, an opening in the ground in a mine. And white is a typical color for aragonite. The other one is also, so all these three aragonites, so the one that we saw, the blue one, this one that I showed you now, or Chris is showing you now, and the one next to it, all three of them come from China. So this looks like frozen fireworks, and this comes from a cave in China. And if you look in detail, so you can see the long needles, but then if you look in the bottom of the case on the so-called pavement of the specimen, it almost looks like fluff, and that is aragonite as well. And that speaks also to the many, many shapes in which the same mineral can occur. If we go back to quartz and amethyst, we can move to the other end of the gallery. You have questions? No. And in the case to the right here, we have another specimen of quartz variety amethyst. This comes from the Anahi mine in Bolivia, and the Anahi mine is actually famous the world over because not in this specific specimen, but I have some in my hand. Quartz can occur in two different colors, both orange and purple. Maybe you can see it better on these cut slice from a bigger crystal. So this is basically a combination of two varieties, amethyst and the brownish orangey one, it's called citrine. And by combining the two variety names, ametrine and citrine, we end up with ametrine, which is the commercial name for this type of quartz. Not only that, but at Anahi, because of this combination of two crystals or more into a single object, the symmetry of the quartz is altered and it forms what's called a twin. So by definition, quartz is always a pointy crystal, as you see in the big amethyst there. Here, this is a complete twin, and on the top, it has a flat surface. You don't see that in untwinned quartz crystals. So this speaks to the huge variety of morphologies that are present in minerals. And speaking of beautiful single crystals, you can have a look at this stunning blue crystal lit from behind. The mineral is zoesite, but there is an amazing deposit of this blue material in Tanzania, and it is called, the variety is called tanzanite. And this has been mined for several tens of years, makes beautiful jewelry. This is a sizable crystal. It's almost 1 kilogram in weight. And until a few months ago, the largest zoesite variety tanzanite crystal known was about 3.3 kilograms. And if you follow the news, this was featured at least on the BBC side. At the beginning of August, a miner at the tanzanite mines in the foothills of the Kilimanjaro in Tanzania found two crystals with a combined weight of 15 kilograms. And just a few weeks later, they found another one with 6.3 kilograms in weight. Those crystals were purchased by the Tanzanian government from this miner for a really nice 7-figure amount of money. Speaking of crystals and of big specimens, we are headed now towards these gigantic specimen of fluoride partly covered by a quartz crust. This comes from China, and it is now the heaviest specimen in the collection. It weighs a whopping 3,329 pounds, roughly 1.5 metric ton, or the weight of a small car. And it has been covered by much more quartz. So the white material on top of the crystals is quartz. But it has been prepared so that it shows the fluoride as well in its beauty. And the very interesting thing is that on the crystals that are still covered by quartz, one can make out much easier the crystal shape. So you might see some rhomb faces under the white coating. And that's a rather unusual crystal shape for fluoride. Fluoride usually it's either in cubes or in the shape of two pyramids that are sharing a base. So thanks to the coating, the quartz coating on the fluoride in this case, we can see that unusual shape of the crystals. Crystals come and specimens come in all sizes. So we have the 1.5 metric ton behemoth, but we also have these beauties which are centimeters in size. And they are called, if they are about 1 inch in their maximum dimension, they are called thumbnail minerals. Some of these are thumbnails, some are a little bit bigger. But irrespective of the size or of the categorization, they are just pure beautiful. A wonderful description of this case was given by a father one day when I was spying on our visitors to enjoy their reaction. And this dad walked past this case with his children, and he just pointed at the case and he said, "Look, baby minerals," which is, I guess, an appropriate description as well. So some of these minerals have a property that's called fluorescence. So when they are, not yet, Nicole, wait a minute. So when they are excited by a specific light wavelength, they emit a light of their own. So we'll look at 2 specimens here. So one will be number 33. Those green crystals on number 33 are emerald crystals. So the mineral is beryl variety emerald. And then we'll look at number 59, which is a glass opal. So I have a blue light pointer here, and you see the red. Okay, now I hope you can see the red of the emeralds under the blue light. And then if we go to the opal, we get these green, neon green color. So in the opal, that color is determined by tiny amounts of uranium that the atoms are reacting to the excitation of these wavelength of light. Whereas in the emerald, that color is determined by the tiny amounts of vanadium and chromium in the crystal. Thank you, Nicole. Speaking of colors, here we have another stunning specimen. And the specimen itself is a fossil. It's an ammonite from southern Alberta. But all fossils are minerals, and this specimen is astonishingly beautiful because of its mineral composition. So this is the inner part of the shell of the animal, which is now made up of very thin packets of aragonite, another aragonite variety. So this is the 4th one that we see here in the gallery. And those layers of aragonite in the shell are basically breaking the light into its components. So white light is basically made by different light wavelengths. And you can see that best, for instance, in a rainbow. In this case, the role that the water droplets in the atmosphere play for creating the rainbow is played by these tiny plates of aragonite. Another specimen that I would like to point to is one of our historic specimens in the next case. So it's this silvery surface that comes just about 20 miles west of New Haven from a quarry in what used to be Branchville. Today it's called The Branchville is part of the town of Reading. And this specimen came out at in about 1870, when two of the professors at the Sheffield Scientific School and at Yale College were working in that quarry. They described 8 new mineral species. And these, what is called pinball muscovite, because it's almost spherical, it's a very rare morphology for muscovite. Muscovite, which is a mica, is usually in very thin plates that can be detached very easily. Mica has perfect mineral cleavage. But at Branchville, it occurs in these pinball morphology. And from here, let's move to some gemstones, because natural gemstones are just polished minerals. So in this case, we have an amazing array of diamond rings, ruby jewelry, rings, necklace, earrings, sapphires, emerald, and opal. And again, some of these are fluorescent. So what happens with fluorescence is, in certain chemical elements, when excited by the light in a beam, either black light or blue light, as the one that I have here, electrons closer to the nucleus are ejected. And that vacancy created is filled out by another electron falling from further away from the nucleus. And that process of filling the void generates energy, which is emitted in the form of color, of fluorescence. So it's basically visible light. The mineral or the chemical element is excited, in the case of black light, by light that we cannot see. We can only see light between 400 and 700 nanometers in wavelength. So these are below 400 nanometers, and it makes the chemical elements emit visible light. Paper is fluorescent. Tooth enamel is fluorescent. Cotton is actually fluorescent as well. So I will focus on the yellow diamond there in the middle, and then move on to the ruby ring, the sapphire, the emerald, the opals under it. So that's what happens with the yellow diamond when it fluoresces. The ruby, it's like somebody turns the lights on inside. And you see on the side of the ruby some other fluorescence. Those are 2 diamonds on the side of the ruby. Then the sapphire is fluorescing as well. The emerald. And then the opal in this light blue color. The opal has another property. So if you pay attention, when I take the light away from it, you might be able to see a streak of light that persists after that. I don't know if it is visible or not.
It is.
I hope it is. And that's phosphorescence. When that state of excitation of the chemical elements persists a little bit after the exciter is removed. Because I mentioned the gemstones in this case, but we don't have the minerals from which these gemstones were carved, let's move to this case with 2 stunning specimens. So I'll start with the one on the right, which looks kind of like a skyscraper. That's a gypsum crystal from a very famous gypsum occurrence in Nica, in the state of Chihuahua in Mexico. And there was a lot of research on gypsum crystals from NICA because back in the early 2000s, in 2005, 2006, a huge cavity in the mine, so this is a mine actually, it was a mine for lead and zinc. The biggest known gypsum crystals were discovered. 33 feet in long, or 11 meters, and up to 1 meter across, or 3 feet. This comes from a higher level in the mine, and this was discovered in the early 1980s. Do we have questions? And next to it is a beautiful slab of a dark rock, which is very rich in carbon. It's called graphite. So that rock is graphitic schist. And the stoplights in it are garnet crystals. So this specimen has been specially prepared. It has been thinned so that it exposes the garnets on both sides. And then behind the slab, there are several strips of LEDs to light it through and to show its beauty. And those are gem quality garnets. So here are some cut, maybe down in the light, I don't know. Cut gemstones, garnet gemstones from that occurrence that we have up there on the back of this case. And I think I'm out of time.
Nicole, do we have any final questions?
Yes, thanks, Stefan. This has been really great. We do have a couple of questions. Today we've seen a number of minerals that are on their own and another number of minerals that are together with some other formation. We have a couple of questions about why that might be the case. Can minerals form with any other mineral? Are there certain kinds of minerals that tend to form together? Can you say a little bit more about that?
Absolutely. So no mineral forms on its own. It's always in an environment in which it's accompanied by other minerals. Now, for display purposes or for certain collectors, individual minerals are more attractive. Personally, I prefer minerals that are together with other minerals because that tells me a little bit about the environment in which these minerals form. So even when we have, for instance, what's called floaters, sometimes quartz crystals seem to have formed without anything around them. Think of Herkimer diamonds. So Herkimer diamonds are found in upstate New York, and many times they are displayed individually. Well, they form in vugs in the country rock, which is a carbonate rock. We actually have a Herkimer diamond crystal on display, but I didn't point to it. Should we? So in the thumbnail case, there is a beautiful one, which also has hydrocarbon inclusions that come from the sedimentary environment in which it forms. So it's number 36. That's a Herkimer quartz crystal. And they are called diamonds because especially the smaller ones are almost flawless and they are very sparkly. And by analogy, obviously, neither the crystal ordering or the chemical composition is that of diamond, but just by analogy, how sparkly they are called Herkimer diamonds. But as I said, I prefer minerals in context with their brothers and sisters when they form. There are other instances when quartz forms, it's found actually in clay in the mines. But that means that the other minerals that were with the quartz when it formed have been altered to clay minerals. So they always form together with something else.
Thanks, Stefan. I have one more set of questions that I want to ask together, and this is about how we put exhibits like this together and what's happening to these specimens in the renovation. Are these minerals and gems going to be on display again? And how do we move them? That seems like a big project, and a lot of them seem quite delicate. Do they ever break in transportation?
So I will give you first the light answers. So how we put together an exhibit like this with great love and care. And about transporting something like this, very carefully. So this is a combination, the way that this exhibit was put together, it's a combination of the imagination and knowledge of many people. And critical to this was actually Dave Friend, who not only provided the funds for this, but he had this vision. So we worked closely with Dave, with our exhibits department, with lighting designers for bringing out most of the beauty of these specimens. In terms of transportation, yes, they are very delicate. Some of them are really delicate, and extra care and also knowledge is needed to transport them without damaging. Of course, I'm sure damage in transit happens. Fortunately, none of our specimens have been damaged when they were transported to the museum. In terms of the renovation, the specimens that are Yale Peabody Museum specimens will go into storage. The specimens that are on loan will go back to the lenders, and when we reopen in 3 years, we'll have a different set of specimens on display. So that is the idea, actually. One of the ideas behind the David Friend Hall is to rotate specimens so that we keep the interest alive with equally beautiful, stunning specimens, and we have people come back. And hopefully by that time, we can meet in person in the museum.
Thank you very much, Stefan. Very informative. We really appreciate it. I'm going to relieve you of your duties as tour guide now.
I just want to say one more thing.
Please.
Everybody, including you two guys, remember that we started with that chunk of dark, uninteresting rock from 4.57 billion years ago. Everything started with the protoplanetary disk. I hope everybody has a wonderful weekend.
Thank you, sir.